Okay, in this lesson, we're going to learn about two important gas laws, things we've seen already in the demonstration, the FET that we looked at, but we're going to look at them a little more closely today. And those two laws are Boyle's Law and Charles's Law. As with all these laws, I'm never going to make you memorize the names of the laws, but you do have to be familiar with their properties and with the dependencies of the variables that are involved. As we said back in the beginning of this unit, all gases can be described. I need my pen. All gases can be described by four properties: pressure, volume, temperature, and the number of moles, which we're going to call P, V, T, and N. And what we're going to do in the next couple of lessons is explore how these variables change and how changes in one will affect changes in one of the other variables while keeping the other two constant. That way we can pull out of kinetic molecular theory. And we're going to tie this into kinetic molecular theory later on, how all of these are interrelated. So in this lesson, first one we're going to look at, first law is Boyle's Law, which is looking at changes in pressure and volume as we hold temperature and the number of moles constant. From kinetic molecular theory, we remember that the pressure of a gas is given by pressure is equal to force over area. And as you remember, increasing the volume increases the area. And so when you increase the area, increasing the denominator, the pressure is going to decrease in order to keep everything equal, and decreasing the volume. So if we decrease the denominator, that's going decreasing the volume decreases the area, and so the pressure is going to increase. Thus, the total force is going to remain unchanged. The total force is unchanged, but the area that it goes over is going to be different. Remember, the total force depends only on the temperature, the mass, and the number of gas particles, and none of those are changing. So notice that the force and the pressure and the area go in opposite directions. As the pressure goes up, the volume goes down, and as the pressure goes down, the volume goes up. And that we can see in this diagram on the right, that if we take the pressure of 1 atmosphere and double that pressure to 2 atmospheres, then we're going to take the volume and we're going to decrease that volume by a factor of 2. So we multiply that by 2, and we're going to multiply that by 1/2. And that's an inverse relationship. So we say that pressure and volume are inversely proportional. And we can draw a plot for that. And that's what the plot on the left looks like, where the plot of volume versus pressure. Now, in this plot, we put pressure on the x-axis. In your lab, you're going to put pressure on the y-axis because, as we discussed in class, and I believe it was Izzy who mentioned it, the pressure isn't going to be what we think it is. We needed to add back in the pressure of the atmosphere, and we don't know what that is in terms of books. So we're going to put the pressure on the y-axis and the volume on the x-axis to make things look good. Okay, so since pressure and volume are inversely proportional, pressure, it turns out that pressure times volume is equal to some constant K. I'm just going to call it a K. It doesn't matter what the K is. And what that means then is that we can rearrange this and find that the pressure is equal to K over volume, or the volume is equal to K over pressure. And that's why we call this an inverse relationship, because the X value becomes either 1 over volume or 1 over pressure. And that 1 over volume, that's what you're going to be seeing in your lab, where X is equal to 1 over volume. In this particular graph that we see down on the right, we have volume versus 1 over pressure. So we've taken the pressure from here and divided or taken 1 divided by the pressure, and see that we show a straight line, and the straight line is going to have a slope equal to k, and k really just depends on, we don't need to know what it actually is. It depends on a couple of factors, but it depends on the temperature and the number of moles of gas that you have, and that's where those would come in if we wanted to go ahead and calculate them. Now, at any point along these lines, since the slope is constant on the right, that means that volume and 1 over pressure are related to each other. But at any point along this curve, I can pick any 2 points and call this one P1 and V1. I can call this one P2 and V2. So if the pressure and volume change, the K is still going to be constant anywhere along there. So we can set those two equal to each other, and that can be written as P1 times V1 is equal to P2 times V2. And this is the functional form for Boyle's Law that we're going to use. So a particular problem is going to give us all of these variables except for one, and I want you to rearrange to find what you're missing. So suppose we have a gas sample that's at 3.5 atmospheres pressure. By the way, hopefully I'll keep all the pressures in the same units. You shouldn't have to convert and cite likewise all the units. That has a volume of 2.5 liters. So let's call this one P1 and the volume V1. And I want to know what the new pressure is. That's going to be my P2 that I'm looking for when the volume is compressed to 1.1 liters, and that's my V2. So I'm going to take my equation, and one of the things I want you to start doing is, rather than plugging the numbers in right away, rearrange and solve for what you're missing. So since we're trying to find V2, let's divide everything here through by P2. And if we divide everything through by P2, we're going to get that V2 is equal to P1 times V1 divided by P2. And we have that relationship now. I didn't want V2. I'm sorry. Let's go back. Somebody should have caught me. Let's go back. We wanted V2, didn't we? Oh, we did want V2. No, I wanted P2. I wanted P2. So we're going to divide this through by V2. My apologies. And we're going to get that, that P2 is equal to P1 times V1 divided by V2. And notice what's going to go on here. V2 went down, so the pressure should overall go up. And let's make sure that happens when we plug our numbers in. So now let's plug our numbers in. P2 is equal to, P1 was 3.5 atmospheres. V1 was 2.5 liters. Notice that the two that go together are, the two properties that are together are going to stay together in the equation. Divide that by 1.1 liters. The liters are going to cancel out. Let's change to a different color. The liters are going to cancel out. And when you do this, we get 8.0 atmospheres as our final answer. And as expected, the pressure went up when the volume went down. Okay, so always do that little reality check. Make sure it works right. The biggest mistake people make in here is using the wrong equation, using an equation that looks like the next equation. So please try to avoid those mistakes. The next law is Charles's law. In Charles's law, we're going to explore changes in volume and temperature, holding pressure and the number of moles constant. So let's go back and look at kinetic molecular theory. As the temperature of a gas increases, and we can put decreases here, everything will be opposite. As the temperature of the gas increases, the speed of the particles increases, and so the number of collisions and the force of each collision both increase. All right, so we're seeing the numerator now is going up. But we want to keep pressure constant. We have to hold pressure constant. If the force goes up, to keep pressure constant, then the denominator, the area, must also increase. and it's going to increase by the same factor. So, or if we go decreasing, it's the same thing. So the temperature and the volume move in the same direction. And as you can see over here, I kind of went the other way, but let's say we start at 1 atmosphere and 400 Kelvin. I'm sorry, no, we don't want to go that way. We want to start at the 1 atmosphere and 200 Kelvin. And you'll see why we're using Kelvin in a little bit. And if we double the temperature to keep the pressure constant, we're going to go from 0.5 liters up to 1 liter. And so both of those go up by a factor of 2. So since volume and temperature are directly proportional, so this is a direct proportion, we can write that the volume is equal to some K times T. This is a different K now, but it's some K times T, or that the volume divided by the temperature is equal to K. And that's going to give us a straight line plot, which we're going to see on the next curve. So if you look at the first form of the equation there, that's actually a straight line with a y-intercept equal to 0. Now, our y-intercept equals 0, but our x is going to be slightly weird. So on the left, we have a plot of the temperature of a gas on the x-axis and the volume on the y-axis, and we do see a straight line, but the intercept is really strange. First of all, we're looking at an x-intercept. The reason we're looking at the x-intercept here is because we can't go down below 0 volume. This is the minimum volume. There's no such thing as negative volume. Yes, I know there's negative space in art, but this is not what we're talking about. We're talking about if you take and go back to that syringe I had, if I squeeze that syringe all the way down to 0, I can't get any less than 0. So what this did is it gave scientists the concept of absolute zero. It turned out that for all gases, under all conditions, gave us the same x-intercept. So they all gave us, no matter what the gas was, they gave us this x-intercept of negative 273 degrees Celsius. Well, that meant that since you can't get down below 0 volume, and that means that there must be no motion because there are no collisions to give us the volume, to give us the pressure. That means all motion must stop. And therefore, that gives us the concept of absolute zero. So if we call 0 Kelvin the absolute temperature scale, negative 273 degrees C, and we just take that and we add 273 to everything on the x-axis, we're going to get an xy intercept of 0, 0. And that's going to give us the direct relationship that as we move along here, we have the slope equal to that k that we had before. And at any point along this curve, the volume over the temperature is equal to that slope k. For all gas problems, and this is going to be something in class we would keep repeating this over and over again, and we're going to do it on Wednesday when we meet. What do you do with the temperature when you have degrees Celsius and when you have any gas problem? I don't care what that gas problem is. You must use Kelvin. You must convert to Kelvin first, no matter what else you do. And you're going to convert to Kelvin. Kelvin is always going to be degrees C plus 273. Always going to add because you need a positive number. Even if your final answer is in degrees C. So you're going to convert to Kelvin first, and then you're going to convert back. And to convert back, just subtract 273 from the Kelvin answer to get to degrees C. And on the homework, you'll see a couple of those. So as I said, if the volume or temperature change, then we're still going to have the same constant. So we're going to rewrite this as our functional form, that V1, let's say this is V1 and T1 here, and this is V2 and T2 here. that V1 divided by T1 is equal to V2 divided by T2, since those both equal the same constant. So here's a typical VT problem. Oh, not sure why that reduced the size. Hang on a minute. Let me put that back up to 160. So first thing, before we even get to the calculations, the first thing I want you to do is notice that you are given degrees Celsius. And so we're going to take that degrees Celsius and we're going to say T1 is equal to 25.0 degrees C plus 273, or 298 Kelvin. By the way, there's no degrees sign in Kelvin. If you put one in, I won't mark you wrong, but you'll never see me putting it in. And you're going to see 298 as a very common temperature, because that's room temperature. And T2 is negative 50.0 degrees C plus 273, and that equals 223 Kelvin. Okay, so now we have our V1, our T1 and our T2. We also have our V1, and so we are trying to find V2. This is a little easier because it's in the numerator. If you have a T2 you're trying to find, you're going to have to be careful not to solve for the inverse. So let's see how that works. Actually, we can rearrange. Let's cross multiply, and we're going to get that V1 times T2 is equal to V2 times T1. And so now we can just divide through by V1 to find the T2 that I'm dividing through by T2, aren't I? I want to get T2 in the denominator. I did it again. Or divide through by T1 because I want V2. And what that's going to give me is, dividing through, I'm going to get that V2 is equal to V1 times T2 divided by there's the T1. I guess I'm a little tired today. And so notice that as T2 went down, V2 should also go down because T2 is in the numerator. And let's make sure that that works. Let's plug the numbers in. Okay, where's my cursor? Let's plug those numbers in. So V2 is equal to, V1 was 4.5 liters. T2 was 223 Kelvin divided by 298 Kelvin. Let's cancel out our Kelvin, and we see that we have liters left over. That's good. That's what we want. And the calculation tells us that V2 is 3.4 liters. Please do that calculation. And notice that the temperature went down and V2 did go down. And so we're all good to go. So the homework is going to be homework 14-1. And I noticed that since we don't have anything else to do tomorrow except the Boyles Law lab, I'm going to make the homework due on Wednesday before class rather than on Tuesday. That'll give you a little extra time to work on this and to maybe hopefully make sense of the Boyles Law lab as well. All right. Happy working, and I will see you on Wednesday.